Hello everyone, welcome to the PUFacademy lecture. In this chapter, we're going to look at the rules and standards for algorithms and key lengths, NIST 800-131A. These rules directly connect to what we discussed earlier, especially about CAVP. What is NIST SP 800-131A? It's a guidelines for transitioning to stronger cryptographic standards to ensure data security. Let's look at the overview first. The primary focus here is providing detail about the transitions associated with the use of cryptography. This involves planning for two main changes. First, the transition to the use of cryptographic keys. This means selecting and defining the process of moving from one key type or length to another based on different cryptographic algorithm. Second, the transition to algorithms. This involves planning the shift from using one cryptographic algorithm to a newer, usually more secure one. Beyond these two specific transitions, the overall goal is to plan ahead for possible changes in the use of cryptography. Technology and security threats evolve rapidly, so being prepared for future shifts is essential. This guidance is aligned with the SP 800-57, which is the standard for key management. This guidance is aligned with the SP 800-57, which is the standard for key management. The approach for transitioning has been addressed in Part 1 of SP 800-57. It makes sure a secured and well-managed cryptographic key. Now let's look at the example of recommendations. It breaks down these standards into two primary categories: algorithms for encryption and decryption, and algorithms for digital signatures. First, looking at the encryption and decryption using block cipher algorithms, we see DDES, which is governed by SP 800-67. This document provides guidelines for its transition and eventual deprecation. Skipjack is specified under FIPS 185. Crucially, the AES, the current industry and government standard, is defined by FIPS 197. This is the key document for modern symmetric encryption. Second, for digital signatures, the DSA is specified in FIPS 186. ECDSA is an advanced method governed by FIPS 186 and the accompanying SP 800-186. Finally, the widely used RSA signature method is also defined under FIPS 186. This visual serves as a quick reference, showing that the selection and implementation of any approved cryptographic method, whether for protecting data like AES or for ensuring authenticity like RSA or ECDSA, must be traced back to a specific mandatory NIST or FIPS publication. This structure is essential for maintaining a secure and standardized cryptographic environment. This slide provides a critical overview of the approval status of symmetric algorithms used for encryption and decryption, reflecting the necessary transition in cryptographic standards. The table clearly outlines the status of various algorithms, highlighting those that are being phased out and those that are currently approved for use. Focusing first on the triple data encryption algorithm, or TDEA, often known as triple DS. Two-key TDEA for encryption is now disallowed, and for decryption it is limited to legacy use. This signals a mandate to stop using it for new applications. Three-key TDEA for encryption was deprecated through 2023, and is now disallowed after 2023 for new data protection. Its use for decryption remains limited to legacy use. This timeline shows the urgency of transitioning away from this older standard. The slide also notes that skipjack encryption is disallowed, with its decryption only permitted for legacy use. Now let's look at the accepted standards. AES. Regardless of the key size, all are currently deemed acceptable. AES 128 and 192 encryption and decryption are acceptable. And the strongest standard, AES 256 encryption and decryption, is also acceptable. This slide shows the clear shift away from older, weaker algorithms like TDEA and skipjack, and the full endorsement of the modern, robust AES algorithm across all three key lengths, 128, 192, and 256 bits, as the acceptable standard for current encryption and decryption needs. This slide is crucial as it details the approval status of algorithms used for digital signature generation and verification, which is governed by the required security strength. The table is structured by two main processes: digital signature generation and digital signature verification. First, let's examine digital signature generation. For any generation process utilizing less than 112 bits of security strength, the status is disallowed. This strict rule applies to DSA with non-compliant domain parameters, ECDSA where the key length is less than 224 bits, and RSA where the key length is less than 2048 bits. Conversely, for all signature generation processes achieving 112 bits or greater of security strength, the status is acceptable. This requires DSA to use specific domain parameters, such as 2048/224 or 3072/256, ECDSA or EDSA key length to be 224 bits or greater, and our SA modulus length to be 2048 bits or greater. Second, let's look at digital signature verification. While the stringent requirements for acceptable verification mirror those for generation, requiring 112 bits or greater security strength, verification includes a limited category of legacy use. This legacy use status is granted only to verification processes that use DSA with parameters indicating lower security, ECDSA with key lengths between 160 and 224 bits, and our SA modulus lengths between 1024 and 2048 bits. In essence, this slide clearly defines the security baseline. For new digital signatures, the minimum requirement is 112 bits of security, driving the mandatory transition to longer key sizes like 2048-bit RSA and 224-bit ECC keys. Thank you for watching PUFacademy lecture. We look forward to seeing you again soon.